announcement from Tom Hess. Was the person who borrowed the Windows 7 DVD, please return it to Tom. So I hope the person who borrowed it came today. In any event, you guys talk with each other, I hope. So I would ask you to talk to your friends and just explain, copy the DVD what you want, but just return the original to Tom so that he can lend it out to other people so they can copy it. By the way, my friends among the Chinese graduate students in physics from Dan were able to copy it, so it was amazing the stuff they could get for me. All right, so first, huh?
Really be saying it with camera?
Yeah, well, it's the stuff they got from me was not the stuff that the Justice Department cares about, which is Hollywood movies and popular music, with things more to do with science. All right, let me start with asking whether anyone has a question. Yes.
Are there any more problems on the homework due Wednesday?
Brilliant question. I added one problem that's a little bit similar to the, let's see, the person aiming the camera also gets chocolate. I added one problem, but and I hope it's not too much.
When did you add it?
I added it this afternoon.
Okay.
And let me just say that on Wednesday I would certainly entertain happily any request for deferring the homework to the following Monday because of the fall break, or the fact that I didn't add the second problem until 4 o'clock this afternoon.
And debate Tuesday.
There's
And
a
there's a
debate
debate
tomorrow.
Tuesday night.
Yes, there's a debate tonight.
Tuesday.
Tuesday night. Right, so you guys have all the reason in the world to postpone the homework. All right, so let me, if I can find some chalk, get started on this. So we got to a certain point last time where I had basically derived that the Feynman propagator at x was a Heaviside function of x0 times something called delta plus of x plus a Heaviside function at minus x0 delta plus minus x. So we had gotten to that point, and of course this thing minus I df is, I'm fiddling here because I want to get the right sign. It's minus I d4 q over 2 pi to the 4th e to the I qx over q squared plus n squared minus I epsilon. Let's see, at least one person who uses the videos has asked me not to open the windows, but because of this background noise from Lomas, but if I hear another cough, I'm going to open the windows because we don't want to be in the, we don't want to get sick. All right, well, let me now show that this, we saw that this in fact is essentially the time-ordered mean value in the vacuum, the time-ordered product, but we saw that from a path integral point of view. I want to now show it from an operator point of view. And first of all, let's remind ourselves what this time-ordered product is. And in fact, when I say it's the mean value in the vacuum, the time-ordered product, I'm talking about the free theory. That is to say, the theory where the Hamiltonian is simply quadratic in the fields, and the time dependence of the fields is given by e to the I plus or minus I kx, which is e to the plus or minus I k dot x minus k0t. This is the kx is just Fourier's representation of things. The k0t is the free field time dependence. So in other words, I'm saying that the fields obey the field equation box plus m squared 5x equals 0. And let me see if I've got, yeah, I've got the signs wrong. That's right. Okay. So this time-ordered product is, of course, theta of x0 minus y0, phi of x, phi of y, plus theta y0 minus x0, phi of y, phi of x. I don't know why I'm writing so fast. And these are fields, in particular, phi of x is an integral a of k, e, and now I've got to get these signs right. I always gag as to whether it's plus or minus, because it's half the time plus and half the time minus here. This is e to the I kx plus a dagger of k e to the minus I kx d cubed k over square root of pi cubed 2k0, and k0 is also called omega k, and it's the square root of k vector squared plus m squared. Okay, well now, what do we have then? If we go into the vacuum and when I say vacuum here, what I mean is that A of k annihilates the vacuum for all k. All momenta k. And okay, so what do we have here then?
That much better.
All right, let's go to.
I just want him to know that the windows are
Yeah,
being
I'm
open.
sorry about this, but we don't want to all get sick. He's protected by the fact that he just watches the video, purely electronic. We have to deal with the viruses. So this is equal to vacuum, well, of course, theta of x0 minus y0, phi of x, phi of y, plus theta of y0 minus x0, phi of y, phi of x. So that's what we have. But now, remember that we were able to split a field into phi plus of x, which is just the first part, a of k e to the I kx, and then this d cubed k over 2 pi cubed 2k0 inside the square root. Phi minus, we can say that this is equal to phi plus of x plus phi minus of x, where phi minus is of x is just phi plus of x adjoint. So in other words, you get a minus sign and a dagger. It's just the second part of the field. That's phi minus. And so the point here is that we've got a phi plus that's going to hit the vacuum. So the only part that survives is phi minus. And we've got here a phi of x, and the only part that survives there is the minus. On the other hand, so in other words, we have the relation phi plus of x on the vacuum is 0, phi plus of y on the vacuum is 0. But we have the adjoint relations, phi minus of x on the vacuum is 0, and phi minus of y on the vacuum is 0. So we can rewrite this as 0 theta of x0 minus y0, phi minus of x, phi plus of y, plus theta of y0 minus x0, phi minus of y, whoops, phi plus of y, phi minus of x. And I got this one wrong also.
Wait,
Yes.
I just want to, I'm a little confused. So is phi plus is the A dagger term? Or
No, phi plus is the A term.
So that seems weird that you call that, I mean, A dagger like plus. I
It's
don't know.
historical.
Okay, yeah.
It's not as bad as in astronomy when people talk about recombination for the first time that electrons and protons got together.
Sorry.
Yeah.
So phi minus of x, the bottom line on the board.
Phi minus of x is phi plus of x adjoint.
Okay, so that's there's like a break between that.
Right. There's a,
Yeah. That's fine.
thanks. Good question. Okay, but now notice what we can do. We can write this as theta of x0 minus y0, and we can replace this term by the commutator. Because when we switch the order, we get 0, because it's between vacuum states. Similarly, we can write this as theta of y0 minus x0 times phi plus of y, phi minus of x. On the other hand, the commutator, in other words, what we have here is A of k, a dagger of k prime, is delta of k minus k prime. And so the commutator of phi plus and phi minus is a number, complex number. And the commutator of over here of phi plus and phi minus is another complex number. So since the vacuum state is normalized, this is just theta of x0 minus y0 times this commutator plus this one times this Heaviside function times this commutator. Now, we have at least my notes here say we have, but I don't remember that far back from class. Yes, we actually computed what phi plus with phi minus is. This was equation 37 in the online notes on coherent, what they call coherent. What we found was phi plus of x, phi minus of y. Well, what is it? Well, it would be d cubed. In the notes I wrote p and q. So d cubed p, d cubed q, 2 pi cubed is 2 square root of q0 p0. Then you have e to the I px minus I cubed y, k of p, a dagger of q. This is delta of p minus q. Is there a question?
Actually, yes. Why is that a function of
Yeah. Ready?
no, I just figured out my question.
Well, why don't you vocalize it anyway and earn your chocolate?
Alright, and I was wondering why we had shifted from, why you were basically using P's and Q's.
Oh.
And I realized.
Well, the alternative is k and k prime or k and p. I mean, it's, the real reason is that I was mousing equations in from one of my documents to another, and it's just the p and q labels. Anything else? Yeah.
So I noticed that from the third line down to the fourth line down, we lose the zero states. What happened there?
What happened to the vacuum?
Yeah.
Well, this commutator, you see, is just a complex number. In other words, this thing here is phi plus of x, phi minus of y. Commutator is just an integral d cubed p, d cubed q, 2 pi cubed, 2 square root of q0 p0, e to the I px minus I qy times delta of p minus q. Because of this delta function relation. So in other words, this is a number. It isn't the remote. These are operators, but their commutator is just a number because we're dealing with free fields. If we weren't dealing with free fields, this thing at different times would be. And so this thing is integral d cubed p over 2 pi cubed 2p0 e to the I, and now p and q are the same, and so this is p x minus y. This is a 4-vector inner product, and this is what we call delta plus of x minus y.
Oh, sorry.
All right, let me make sure that I don't have an I or a sign loose here. Yeah, okay, this is all right. What?
So the delta function is only over the 3-vector.
That's right.
So why are we?
Well, we have a 3-vector integration.
Right, but why are we changing the Q0 into another P0?
Ah, very good question. Because Q0, you see, is square root of m squared plus q vector squared. That's worth a chocolate. You're welcome. Okay, so now we're at the point where we've seen that the mean value in the vacuum of this time-ordered product of phi of x, phi of y is just theta of x0 minus y0 delta plus of x minus y. That's the first term. The second term is the same, but y and x are interchanged. So this, here we just replace x by y, y by x. And so this thing is theta of y0 minus x0, which was the coefficient, and then we have delta plus y minus x. On the other hand, over here, or let me say that last time we had derived this relation. This came from taking this four-dimensional integral, introducing a ghost contour, doing the contour integration, we got this relation. And so this says then that this mean value of the vacuum to time ordered product is minus I delta F of x minus y. And in fact, one could have written this a little bit more succinctly as simply time-ordered product.
Okay, we're recording.
All right, I hope this is the second part of the video. Anyway, let me erase this. So this is our rule, and the mean value of the vacuum time-ordered product 5x 5y is minus I, the Feynman propagator. And this is what we derived earlier in a path integral formulation. So we've sort of brought the two together. Now let me go back to what we were doing with the electromagnetic field. And we were talking about, we were quantizing it in the Coulomb gauge. And is there any question though, as I'm erasing this? All right, let's see. All right, so what we did in the Coulomb gauge was we said, oh, look at that chalk. See, some of this chalk is so much better than other pieces. This was 1 over root 2, r of k, excuse me, 1 plus or minus I 0. And we introduced, we call this epsilon lambda. And we had the commutation relations a lambda of k, a lambda prime of k prime is delta lambda lambda prime delta cubed k minus k prime. And then we had a lambda of k, a lambda prime, oops, dagger k prime equals 0, and the adjoint of that as well. Okay, now, so then we define the electromagnetic field, and let me put in an index this time. AI lambda of x is the sum over lambda equals plus or minus epsilon I lambda of k, a lambda of k, e to the I kx, plus epsilon lambda star I of k, a lambda dagger of k, e to the minus I kx, and then d cubed k over square root of 2 pi cubed 2k0. And k0 here is just length of k because the photon's massless. So you see the structure is the same basically as for a scalar field. The difference is we have polarization vectors here which make this a three-dimensional vector. Equivalent, you can think of this as a 4 vector with 0 as the time component. And that's because in the Coulomb gauge, the time component of the electromagnetic field is not a quantum variable. Instead, it's a dependent variable that's given by that famous integral over the charge density. All right, now, what I want to show you is, I want to do a polarization sum for you. These polarization sums are very important. And in particular, let me just call it MIK, IJ, of K is going to be the sum, lambda equals plus or minus, epsilon I lambda of K, epsilon J star lambda of K. And what I want to do is I want to show that this is equal to delta Ij minus Ki Kj over K vector squared. So that's a nice formula. Now there are various ways of,
Sorry, question.
yeah.
K, is that a function of lambda or x or k? I can't remember.
Whoops, sorry. A only has an index, this vector index,
Right.
and then it has a space-time variable. We're summing over lambda, so lambda is a dummy variable.
Right.
All right, now, what did we say about M? Well, M is Hermitian as a matrix. It's 3 by 3. It has trace 2. And we can say that M on the vector K is 0, and K transpose on M is 0. I think these are sufficient to determine exactly what M is, but let me show you what M is more directly by using our formulas for epsilon. I think this is a good thing to do. Trying to find a piece of chalk that was nice as the one I had. Okay, so let me start over here. M of K, it's a sum lambda equals plus or minus epsilon. I'm using matrix notation now. Epsilon lambda of K, epsilon lambda dagger is what I should have had in my notes. I had. Can I use your pen a second? Thanks. Epsilon dagger of K. And so this is 1/2 sum on lambda R of K, 1 lambda I 0, 1 minus lambda I 0, R inverse of K. Let me remind you what R is. R is a 3 by 3 matrix that takes Z hat into K. So R of K takes Z hat into actually K hat. And there are many rotations that do that. Obviously, you can have a prefactor that's a rotation about the Z-axis, and that doesn't change anything. You can have a post factor, which is a rotation about the K hat axis, that doesn't change anything. So R is not defined uniquely, you just make some convention and you define which of the many rotations we're talking about. But what it has to do is it takes Z hat into K hat. And we will need to know which the choice is. Okay, this is an outer product of vectors, and so this is actually a half sum on lambda R of k, 3 by 3 matrix, and this is a 3 by 3 matrix. And if you're rusty about outer products, here's how it works. You take this guy here and multiply it over there. So you get 1 minus lambda I 0. Then you take this one and multiply across, and you get lambda I lambda squared, which of course is 1, 0. And then this one just gives you 0, 0, 0. But now when we sum over lambda with plus or minus, this one goes to 0 and that one goes to 0. So this is 1/2 R of k, 1, lambda squared is obviously 1, 0, 0, 0, 0, 0, 0, 0, R inverse of k. Now R, of course, is 3 by 3. It's unitary, it's real, so it's orthogonal. The adjoint is the transpose is the inverse. So this R inverse can be thought of as R transpose or R adjoint, R inverse. Now what is this? Well, this is equal to 1/2 R of k.
Why is there still a 1 half?
Why what?
Why half? Why is there still a half?
Still a
Should be good.
good point. I think you're absolutely right. Brilliant. It's because my arm was down. My left arm was down. Let me just check the notes. I think that there's no half. Okay, so what do we have then? What we have is the 3 by 3 identity matrix. And then minus this piece. But this piece is minus z hat transpose R. In fact, let me just call it R transpose just to make things symmetrical. Okay. Well, the first term is R1, R inverse, so that's just 1. This is the 3 by 3 identity matrix. R of k takes z hat into k hat. So this is minus k hat transpose. Okay? And of course, what that means then is that Mij is equal to delta ij minus ki kj over k vector squared. Okay? So that's what the polarization sum is. Now, the second homework problem that I added was to take this, to use this spin sum, which is to say that the sum of the polarization, the outer product of polarization vectors over lambda, that sum is delta ij minus ki kj over k squared. Use that, and you don't need to use very much of it, to show that ai and aj at equal times commute. And that ai dot and aj dot at equal times commute. So that's what the second homework problem is. Okay. So what I want to try to do then is to show you that, show you what happens if we take AI with AJ dot. And All right, so what are we going to have? We're going to have I of x, a dot j of y, and let me specify these are equal time commutators. And x is a 3-vector, y is a 3-vector. So what is this going to be? Well, it's going to be a sum across over lambda integral d cubed k over the square root 2 pi cubed 2k0, and now epsilon I lambda of k, a of k, I kx, plus epsilon lambda star I of k, a dagger of k, e to the minus I kx. So it's all that commutated with sum on lambda prime integral, let us say d cubed k prime 2 pi cubed 2k prime 0 epsilon lambda prime j of k prime, but now there's a dot. There's also a minus sign in the metric. So let me write that as minus I k0. That's what's pulled down by the time derivative. Epsilon lambda prime j with a prime here of k prime e to the I k prime y plus I k0 prime epsilon j star lambda prime of k prime e to the minus I k prime y. Okay, and all right, well, let me make this a curly bracket. Another curly bracket there. Okay. Now, A commutes with, oh wait, where's the A? I left out an A. This is all important. A lambda prime of K prime, and then in here, a dagger lambda prime of K prime. Okay, well, A of K commutes with this A of K, but not with this one. And so what we get as a commutator I don't know if I should write everything down. Maybe I should. Sum over lambda and lambda prime integral d cubed k prime 2 pi cubed 2 square root k0 prime. So that's that. Then the rest of this is going to be epsilon I lambda of k, epsilon j star lambda prime of k prime. And now this commutator of a lambda k with a dagger lambda prime there is going to be delta lambda lambda prime, delta cubed of k minus k prime. But there's an I k0 here. Prime. The next term is going to be a dagger with this A, and that's going to be plus epsilon star I lambda of k and it's going to be minus I k0 prime and then epsilon j lambda prime of k prime. And I left something out, an all-important phase factor. This thing is e to the I kx minus I k prime y. And this is going to be e to the minus I kx plus I k prime y. And the commutator here is a dagger a, so that's delta lambda lambda prime delta cubed k minus k prime, but with a minus sign. All right? Since my left hand is down, you need to be checking me, all right? I didn't have time to latex this. All right. Now, as I've said, as you work through your study of quantum field theory, you're going to come to love Paul Dirac and his delta function. Because we've got a terrible six-dimensional integral, the delta function makes it a three-dimensional integral.
Sorry, I'm not sure if you said it. What were the like terms first?
We're what?
The like terms?
The what terms?
The like terms. Like epsilon I and then
Oh,
epsilon
well,
j.
that's because they would be the commutator of A lambda k with A lambda prime k prime, that's 0.
Right.
Okay, so we have this delta, double delta. So we're left with sum over lambda integral d cubed k, 2 pi cubed, 2k0, because the three-dimensional delta function makes k0 prime equal to k0. We then have here e to the I k x minus y. And then we have epsilon I lambda of k, epsilon star j lambda of k. But then we then have an I k0. And these minus signs cancel, so we get I k0 epsilon star I lambda of k, epsilon j lambda of k, e to the minus I k x minus y. So this is what we have. Now we see that things are turning out very nicely. Because you see the k0 here cancels this k0, and moreover, we've got epsilon star. We've got a sum over lambda of this thing. Well, the sum over lambda, we saw that the sum over lambda of these things is real. Since it's real, we can move the star over here, and we combine the two. So altogether what we've got is sum over lambda, integral d cubed k, 2 pi cubed, e to the I k x minus y, an I out in front. The 2 and the k0 have canceled. We have epsilon I lambda of k, epsilon star j lambda of k. And I'm getting this. I'm getting this. Hold on a second. well, maybe I should write it this way. E to the I k x minus y plus e to the minus I k x minus y. So it looks like this.
So should there still be 1/2 in that case?
Hmm?
Should there still be 1/2 in that case?
You know, I think you're right. Thank you. It's really worth 2 chocolates, but we've had so many I'm worried about diabetes.
Sorry, what did you?
By the way, there's a... All right, when I get to the end of this, I have to change some good stories. All right. The next thing is then I. Now this sum over lambda is quite nice. This is integral d cubed k over 2 pi cubed. 1/2 e to the I k x minus y plus e to the minus I k x minus y. And then this thing is, I don't know if there's room to write it, but delta ij minus ki kj over k vector squared. In other words, it's this thing here written small over there. Now this is an even function of k vector. We're integrating over k vector. This is an even function of k. Here, we've got a k0, but k0 is an even function of k. And consequently, we can just flip k vector to minus k vector, and we just make this minus a plus. And so what we've got is a I of t of x, a dot j of t and y. By the way, since you can tell that what I'm doing today is very close to the second homework problem, right? Huh?
I haven't actually seen it yet.
No, I told you what it was. Didn't I tell you what it was? The second homework problem is to show that AI commutes with AJ and that AI dot commutes with AJ dot. So now what do we have here? We've got an I integral d cubed k 2 pi cubed e to the I k x minus y delta ij minus ki kj over k vector squared. All right, so this is I delta ij delta cube of x minus y. Oh, what I forgot to say, I mean, I said it explicitly here, but you see, there's no, I was talking about a k0 term. There is no k0 term here, because the times are equal. And so over here, it was even easier to flip x minus y to y minus x, is because there isn't any k0. I should have mentioned that.
So, how does that mean that we can just combine these into a single exponential?
I mean, how is it that I could combine this with this and cancel your factor of 2?
Yeah, it's literally just become a cosine of k.
All right. Let me. All right, we have an integral d cubed k e to the minus I, and it's just k vector dot x minus y vector. Okay? And then it's delta ij minus ki kj over k vector squared. Okay? All right. Now, what we're doing is all right, let us just replace minus k, let us set minus k equal to p. And this is just a positive measure, so this goes into d cubed p. Then we get e to the ip x minus y, and now delta ij minus bi minus pj over p squared, or minus p squared. But these minus signs cancel. So, because this thing is even,
So I understand that bit, but.
so it's pi pj over p squared. So you can combine, so this thing is the same as integral e to the I k x minus y delta ij minus ki kj over k squared d cubed k. So these are the same, so I was able to set this equal to that and cancel the two.
Okay, and I understand most of your group, but I don't understand how you're translating d3k into a non-negative d3k. You said something about the positivity, I didn't.
Yeah. Frankly, I'm very sympathetic to your question because it puzzles me every time. It was. All right. What is this integral? This is a sum of this thing over all points in k space. Okay? So in other words, we're summing it over k this way, k that way, k that way, k this way. Okay? So this thing is an intrinsically positive measure. It's just the size of each cube in k space.
So they can't have negative volume.
Huh?
Can't have negative volume.
Yeah.
It's a little bit more sense.
I mean, there are slicker ways of saying it, but okay, so we've got the first term. The next term, though, is a derivative. What derivative is it? Well, it's plus I, and it's two derivatives. It's di, or let me write this more exactly. d2 partial xi partial xj of the integral d cubed k e to the I k dot x minus y over k vector squared 2 pi cubed. Okay? And this is our famous, this is I delta ij delta cubed x minus y plus I partial to partial xi partial xj of 1 over 4 pi x minus y. This is the Green's function for what? Laplace's equation or Poisson's equation? One of the two. The French equation. And this is also called the transverse delta function. Transverse because apart from the ordinary delta function, you've got this screwy term involving all those involving those partial derivatives. All right, any questions? All right, once again, it's story time, and I've got several stories. I might have told you one or two of them. The first one is a joke that went around the Soviet Union before the breakup of the Soviet Union. And it was about the difference between capitalism and communism. In capitalism, man exploits man. In communism, it's the other way around. Okay, that was the first story. The two other stories, I remember one clearly, and the other one has slipped my mind. This other story is a longer story, and it's a true story of something that happened just over 50 years ago. And just over 50 years ago was the Cuban Missile Crisis. I was in college at the Midwest, and I wasn't watching television, and I was blissfully ignorant of the whole damn thing. This was before the internet, you know, so all I had in my room was physics books and a bed, and so I wasn't really aware of it. On the other hand, later when I got to graduate school in the Boston area, there was one graduate student who told me that he was so frightened that he got together and went camping in the mountains in case there was nuclear war because he thought Boston would be wiped out. Anyway, the story is that 6 months or so, or that the CIA, before the Cuban Missile Crisis, had been trying to kill Castro, Fidel Castro. And one of the people they hired was a hero a guerrilla hero in Cuba, who happened to have a beach house right next to Castro's. And this guy was being briefed about, I guess, let us say 6 months before the Cuban Missile Crisis, by somebody who said that he was Robert Kennedy's personal representative. And the mission was to kill Castro, and he'd get the means to do it in 6 months. Well, 6 months went by, it was the middle of the Cuban Missile, it was after the Cuban Missile Crisis. It was, in fact, November, 2 years later, or a year later, anyway, now I'm lost track of it. 1 year later, November, a little more than a year later. And this other person from the CIA, they were meeting both times in a safe house in Paris. And the CIA guy was giving the man a Papermate pen and a syringe and a bottle of poison. And the deal was, what he had to do was use the syringe, take the poison out, load it into the Papermate pen, which had a very fine needle, and all he had to do was brush the needle against Castro's skin, and Castro would likely die. And he was explaining this. The date was November 22nd, 1963. The phone rang. It was a call from Washington, CIA headquarters, and the message in the phone call was President Kennedy had just been assassinated, and the mission to kill Castro was canceled. And later, the CIA found out that this hero this guerrilla hero whom they had been paying as an agent for a couple of years, in fact was a double agent and had been working for Castro all along and had no intention of killing Fidel Castro. So, and then of course the other amusing thing is that, at least as far as I know, Fidel Castro is still alive. Kennedy's been dead for almost 50 years, and almost everybody else who was in charge of him at the time has passed away. One of the lessons, by the way, of the Cuban Missile Crisis is how important communication was. President Kennedy was able to communicate with Premier Khrushchev by several channels, because the United States and the Soviet Union had diplomatic relations, so they could talk to each other and step back from the brink of nuclear war. Well, the lesson from that is that we should have diplomatic relations with every country, and especially countries that we're concerned about, like Iran and North Korea. And so it's just stupid that we don't. Iran. Okay, so the end of the story. Stories. So let's see. I can go in. Now let me go a little bit further in this same direction. And what we've done here is we've seen that what the commutator is of these. In fact, I don't know if I can derive this, or if I can derive this in the time that remains. Let me just perhaps give you the answer. I think it's. Maybe I could. All right, well, let me tell you what the result is. Whether I can derive it on the fly and in the time remaining, I don't know. Minus I delta, and just because I'm copying this from Weinberg's book, where he loves Greek letters, we're going to have some Greek letters here. Okay, what does one get for the, and what is A mu? A mu is for the spatial indices, it's this, and for mu equals 0, it's just 0. Because remember in the Coulomb gauge quantization, we've gotten rid of A0, we've replaced it by an integral of rho of x, rho of y over 4 pi x minus y. Okay. And what is this? Oh, there's a minus I here. I somehow left out the I. And this is an integral then dqp, 2 pi cubed, 2p0, or length of p, times dpip x minus y, theta of x minus y, plus e minus ip x minus y, theta of y minus x. And what Weinberg means by x minus y is really this. And then what? And then there's obviously a mu nu dependence, and mu nu dependence is what he calls p mu nu, and it's just the thing that we derived earlier. Namely, it's right. So really, this is sort of a bit silly here. This is really ij. Let me fix this up because it's a little bit. I think we're making things wholly mysterious here. It's delta ij minus pi pj over p vector squared. Okay. That's what the actual formula is. And then, of course, if either of these were zeros, then you'd obviously have 0 on the right-hand side, because the time order product of 0 times 0 is 0, or the time order product of 0 times aj is 0. So that is the expression, and I suppose I might as well derive it, because Hey, to just reinforce what you've already seen earlier today. I wasn't planning on deriving this, but what will this be? Well, as we did it this is going to be theta of x0 minus y0, and then it's going to be ai plus of x, ajy minus, right? Because if we put in the plus part here, we're just going to get 0. We put in the minus part, we're going to get 0. And remember, these are space indices, so whether they're up or down doesn't matter. And this again is plus, minus, vacuum. Now we can replace these two with commutators, because that's not going to change anything. Okay. So now we've just got the commutator of A plus with A minus. So let me work that out using what we have here. So A plus and A minus. And what we're going to have then is sum over lambda, blah, blah, blah. This is A plus, but we're not going to have this. And what's A minus? Well, let me rewrite A minus here. Or to put it differently, we can put it all on one line here. This is going to be A minus, so this is going to be epsilon J star lambda prime of K prime, A dagger lambda prime of K prime e to the minus I K prime Y. Okay?
With the sum though, right?
We're summing over, yes.
In the integral in K prime.
Well, I better not throw them together sequentially. By the way, that long story that I told you about the CIA, I heard this on what's called C-SPAN 3. They were replaying a symposium, or they were replaying, or perhaps it was perhaps a live broadcast from the Kennedy Center at Harvard, the 50th anniversary of the Cuban Missile Crisis. Okay, and yes, d cubed k prime, 2 pi cubed, 2k0 prime. All right, I think we've got everything now. Now, this thing gives us the delta function we still have a sum over lambda, and we'll have epsilon lambda I of k, epsilon j star lambda prime, k prime, and then we have delta lambda lambda prime delta cube k minus k prime. So that's from the commutator. And then there's the factor e to the I kx minus I k prime y. Okay, well the delta functions make everything so much nicer. We just get d cubed k, 2 pi cubed, 2k0, and now we have sum over lambda, epsilon I lambda of k, epsilon j star lambda of k, e to the I k x minus y. And now this sum, of course, is integral d cubed k over 2 pi cubed 2k0, and this sum is delta ij minus ki kj over k squared, and the phase factor is e d I k x minus y. Okay, so now this thing here is what we call delta plus, or what did I call it over here? What did he call it? Well, it's that we clearly finished. I mean, we've got that. Where are we? This thing is this thing, and so vacuum time of the product AI AJ is then theta of x0 minus y0, and the first term is this one that we just did, namely integral d cubed k over 2 pi cubed 2k0 e to the I k x minus y, and then this delta ij minus ki kj over k squared. And now the next term is, well, it's obviously the same thing, but just with y and x interchanged, right? And so this is a piece of chalk. Look at the difference in the chalk. And its integral okay, so that's what the thing is. And now, if we compare what I wrote down, you see it's exactly the same. So we've derived this expression. All right, we're at the end of the hour. I think if there's a question, let's ask the question and I'll try to answer it. All right. Okay, so let's stop the recording. Can I use